Now let's talk about temporal efficient coding. This is like spatial coding, composed of decorrelation as a Fourier transform now in time, and gain control again for each Fourier component, and multiplexing as the inverse Fourier transform, so that the original input, which is actually now signal as a function of time plus noise, is filtered by a temporal filter, transform K, become the output temporal sequence O as a function of T. You may ask, what is this signal S at time T? You could see it as the luminance value for a particular image pixel at time T. You can also think of it as the average of the luminance value over an image region, or the outcome of convolving a spatial image by a spatial resistive field at time t. In the later lectures, we will combine space and time together. For the moment, let's just focus on time only for temporal coding. It is analogous to spatial coding, except that time t is one-dimensional rather than space as two-dimensional. And the encoding transform kt should satisfy temporal causality, so that the encoded signal OT prime depends only on the past input signal ST, but not on future input signal. For the decorrelation step, we recognize that the signals are correlated in time with this correlation matrix Rs, whose element T prime is defined as this correlation between ST and ST prime. This, of course, depends only on the temporal difference T minus T prime. Therefore, we can write it also this way. And you can imagine that this correlation function decays with T minus T prime. And this matrix should also be a topless matrix. Then, like we did for spatial coding, this decorrelation is a Fourier transform and a transform in time. And so therefore, this is Fourier component for temporal frequency, omega. And in natural scenes, the power of this Fourier component as omega, when you average over all natural scene images, it decays with omega very quickly. And this is also very similar to spatial power spectrum of natural inputs. With this power spectrum, we can do the next step, gain control. And we remember that this gain, G, for each Fourier component as omega, depends on signal to noise. And noise is white noise, so therefore it does not depend on omega. Therefore, this G, gain G omega, for each Fourier component should increase with frequency for small frequency omega when the signal to noise is large, for whitening, for decorrelation, and then decay with frequency for higher frequency omega to smooth out noise. This is very similar again, like the spatial gain as a function of frequency. The third step is multiplexing. It is a Fourier inverse transform so that the resulting temporal filter KT should be such that, as in this example, its value is equal to 0 for t less than 0. This means this output at any time t prime does not depend on any future input st at time t larger than t prime. Yeah, this is not depending on the future, it's a temporal causality requirement. To satisfy this requirement, for this filter, you require a particular phase for each Fourier frequency. And you should choose this phase to satisfy this requirement. And this choice of phase, for example, can be like this, phase as a function of frequency. And this choice one can make as the freedom to choose what your multiplexing matrix U can be. Yeah? And of course, KT should also be real, written like that. So this choice phase should also satisfy this requirement. That means it switches sign when the frequency omega changes sign. In addition to the causality requirement, we also want this latency tau p not too big, otherwise this temporal filter may be lasting too long. So to make the filter peak at this time t, these cosine waves better add up constructively at this time t, and we can achieve this if these phases for different waves all have the same phase value phi naught at this time, independent of the frequency. And this you can achieve by this phi omega function. And you notice that this function decays with omega, yeah? And just like in this plot. And then your filter can be written like this if you plug this phase into that. If tau p equal to 0 and phi naught also equal to 0, then KT will peak at time t equal to 0. In fact, it will be an even function of time because cosine function is an even function of time. And therefore, it is actually a center surround function peaking at time 0. Analogous to spatial coding, if we recall. Therefore, its value kt will be non-zero for negative time, violating causality. Of course, in spatial coding, causality is not an issue.